All right, students, we're going to be talking today about graphing rational functions. So first we're going to talk about this most basic parent function of the rational functions. A parent function is just the most basic form of that type of function. So this one would be y or f of x equals to 1 over x. That's our most basic one. Now this type of shape that you guys can see it forming is what we call a hyperbola. Okay, it consists of two symmetrical parts called branches. So we've got this branch on the lower end, branch on the upper end. The domain and range are going to be all non-zero real numbers. Now the reason why it says non-zero, notice what is happening at the zeros. Okay, these blue lines keep on getting closer and closer to zero, but never ever actually get there. Okay, and that's because of a property of 1 over x. So think about what happens as x gets bigger. At 4, we had 1 over 4. At 10, we'd have 1 over 10. At 100, we'd have 1 over 100. At 1,000, we'd have 1 over 1,000. At 1,000,000, we'd have 1 over 1,000,000. These fractions are getting smaller and smaller and smaller the bigger that x is, but no matter how big x is, it still doesn't equal 0. So the numbers go lower and lower and lower because the fraction is getting smaller and smaller and smaller, but it never ever reaches 0. And that's why we see it going off like that. Now, as it approaches 0, we see something else interesting. Now, for 1 over 1, it would just be 1. But then if we think of, well, let's do 1 divided by a half. So 1 divided by 1/2 would then give us 2. If we do 1 divided by 1/4, well, that would be 4. So we do 1 divided by, let's say, a 1/10, we'd have 10. As we do 1 divided by 1/100th, it would be 100. So as this gets closer and closer to a 0, which means we're dividing by smaller and smaller fractions, the number gets bigger and bigger and bigger. But once again, because we cannot divide by 0, it'll never ever be able to have a number there. Okay, so that's why we see that the hyperbola has these asymptotes. An asymptote is a value that it gets closer and closer to, but never actually reaches it. The vertical asymptote of this base function is x equals 0. The x equals 0 is this vertical line right here. Okay, and then we also have a horizontal asymptote at y equals 0. So that would be this line right here. Those are the two asymptotes that our equation is going to get closer and closer to without ever actually reaching it. Okay, so the domain and range will be all the numbers except for those values at the asymptotes. Okay, all right. So now we're going to compare two functions. Already graphed here is the graph of 1 over x. Okay, and that table is already filled in. What we're going to do is we're going to graph g of x is equal to 6 over x. And we want to see how does changing this number up top change the actual graph of it. So pay close attention to the changes you see in the graph. So if I were to put -3 into g of x up here, meaning we'd have 6 over -3, well, that would equal negative 2. 6 over negative 2 would be negative 3. 6 over negative 1 would be negative 6. 6 over 1 is 6. 6 over 2 is 3, and 6 over 3 is 2. So now we've got these points that we can start graphing. All right, so negative 3, negative 2. There's our first point, negative 2, negative 3. And then negative 1, negative 6. So we'd be all the way down here. Okay. So what we're going to have is approximately something that looks like that, at least for the left side. Once again, we still have our vertical and horizontal asymptotes that are at y is equal to 0 and x is equal to 0. Okay, so our purple line is going to be getting closer and closer to those dotted lines, but never actually touching it. Now for the positives, at 1, it should be up at a 6, at 2, up at 3, at 3, it would be at 2, and once again. Now, what this essentially did was kind of a vertical shift. Okay, all the dots on our purple line are going to be 6 times higher than, or 6 times lower, depending on if the vertical was, or the y value was above or below. But notice this dot was at 1, up there it was at 6 times higher. This one was at 1/2, this dot was up at 3, it was still 6 times higher than a half. Everything on this line is just 6 times bigger than that one. And so by changing A, we create what's called a, there's a dilation effect here, okay? Or a vertical stretch. So this has been vertically stretched by a factor of 6. So let's also look at another type of transforming this function. So here we've got this function, which is a big change from just the a over x. We already know that a shifts it, or a vertically stretches it. But what do h and k do? So over here, what h and k are going to do is they're going to create new asymptotes. So rather than our asymptotes being at x equals 0, y is equal to 0, our new asymptotes will be at x equals h and y equals k. So that's where we're going to get these new asymptotes. It's going to move where those are at. Now before, our vertical asymptote was always at 0 because we can never have the denominator be 0. But if this is x minus h, then x would have to equal h for the denominator to be a 0. So that's why that asymptote gets shifted over to wherever h is. We've got y is equal to k. If you add a number to a graph, that's going to move it up. So our original asymptote was at y equals 0. Well, if we add a k to it, everything will go up k places, including the asymptote. We're going to plot these points to the left and right. So then for step 2, after you've drawn the asymptotes, step 2, we're going to plot the points to the left and to the right of the vertical asymptote. So that's what you see here. This person, in order to draw this graph, did about 3 points over here to the left of that vertical asymptote and about 3 points over here on the right of the vertical asymptote to give them a good idea of what the shape of this is going to be. All right, so here we've got this function right here. Now let's go ahead and label some of our numbers. We have a, which is going to equal a -2. We're going to have h. So let's look at where h was. We had minus h up there. Here we have -1. So h must be a 1. And then k looks like it must be a 3. So we're going to use that information to now begin some of our asymptotes. So our first asymptote should be x equals h. So I need an asymptote where x equals 1. Actually, let's put that right there. So over here, x is a 1 along this dotted line. Okay, then for the horizontal asymptote, we have where y is equal to k, or in other words, where y equals 3. So that's going to create that asymptote right there. So now we know where those are. Now we're going to pick some 3 points to the left of our vertical and 3 points to the right of it. And I'm just going to go ahead and draw a table right here. So our vertical asymptote is here at a 1. So I want 3 things to the left of 1. So I'm going to right now just pick -3, -1, and 0. And it doesn't have to be these. You can pick any number. I chose these because I think they give us a nice appearance, but if you chose different numbers, this still works. Now we need some to the right of a 1. So I'll go 2, 3, and 5. So if I put a -3 in for x over in this equation, we would then get out 3.5. If we put in -1, we get 4. If we put in 0, then we will get 5. For 2, we get a 1. 3, we get a 2. And at 5, we're at 2.5. So let's go ahead and start graphing those points. At -3, we're up at 3.5. At -1, we were up at 4. And then at 0, we were up at 5. Now notice, I can already see how that's going to line up and how we're going to get closer and closer to our asymptotes without ever touching. Then at 2, we should be at 1. 3 would be at 2. At 5, we'd be at 2.5. And once again, I can see what kind of shape is going to be coming out of those points. Okay, so that was step 3. We drew the 2 branches of the hyperbola so that they passed through the plotted points and approached our asymptotes. Now, writing our functions the way that we did up here in this format, a over x minus h plus k, that's not the only way these equations could occur. So we could see it look like this. Now, our vertical asymptote is always going to happen where the denominator equals 0. Just like when we solved for excluded values, whatever value would have to be excluded, these places where x is a 0, these are places where you're going to have a vertical asymptote. There are some exceptions, such as holes rather than asymptotes, that will be discussed in a later video. Okay, but what's going to make this 0? So if I had cx plus d, I want to know when is my denominator going to be a 0? Well, we could minus the d from both sides. Then we could divide by the c. And so it would equal 0 at negative dc. So that's where this vertical asymptote comes from. We'll have a vertical asymptote at x is equal to negative dc. The horizontal asymptote is going to come from y is equal to a over c. Okay, so those two numbers are given right there. So we're now going to use this new information to be able to draw these graphs. All right, so once again, I see my A is equal to a 3, B was equal to a negative 1, C, it should be the number in front of X, we don't see 1, so it's 1, and D is equal to 2. All right, so first, let's go ahead and find our two asymptotes. We should have an asymptote at x is equal to negative d over c, which should be negative 2 over 1, or in other words, negative 2. So where x is at negative 2. Now notice that was at 4, so halfway between 4 must be negative 2. So that point right there, just be careful and look at the way graphs are labeled. That was not a negative 1, that was a negative 2. All right, so now we've got our vertical. Let's go ahead and figure out the horizontal. The horizontal should be at a over c, so that should be 3 over 1. So we want a horizontal there at 3. And because our vertical was here at negative 2, notice we've got 3 numbers that are lower than a negative 2 and 3 numbers that are higher than a negative 2. So we can get a good feel for the shape of this particular graph. So as I start filling in those numbers, if I put a negative 9 in for x, we will get 4. Put in negative 4, we get 6.5. I would advise you at this time to pause the video and try and make sure you're calculating the same numbers as me, just as a quick check and making sure that you are doing this correctly and you know how to use the calculator that you have chosen. So at negative 3, it would be a 10. At negative 1, negative 4. At 0, we will get negative 0.5. And at 5, at 2. All right, so at negative 9, we should be up at 4. At negative 4, up at a 6.5. Okay, at negative 3, we would be up at 10. All right, so that right there helps me a good amount to know what shape I'm creating. And then negative 1 would be down at negative 4. 0 at a negative 0.5. And 5 would be up at 2. So once again, those 3 points help me to draw the shape of my hyperbola really well. Now, these two equations, the y is equal to ax plus b over cx plus d, notice it created the same kind of graph that we got from a over x minus h plus k. Both of these are just forms of the reciprocal function. They are rational functions. And so what we're going to look at now is the way that these two are actually the same function. We can rewrite the rational function to reveal different properties of the function. For example, we can rewrite this rational function, a over x minus h plus k, and we can see that it's a translation where we saw it went up k and it went over some x minus h places. And so what we're going to do is we are going to, sorry, I know I didn't describe myself very well right there. I apologize. What we're going to do with this next example, we're going to take this g of x. We are going to change it. We are going to do some manipulation of that equation to change it into this form so that we can then see how it's related to that original. Remember, we already figured out that a gave us a vertical stretch. We know what a does in this equation, but what specific function do k and h perform? Okay. Now, one thing to keep in mind as we do this is that when we did this most basic function, it always had the asymptotes being where x is 0 and y is 0. So we're going to want to pay close attention to how did those asymptotes change based on our new graph. But we want it to be in this form. So first, looking at this equation, we notice that it's division. Well, we've done division before, so I'm just going to go ahead and use synthetic division. This should be simple because we don't have many numbers here. Negative 2 times 2 will give us negative 4, and we're left over with 1. So that would create the equation of 2 plus, and then our remainder, 1 over the x plus 2. Which we can go ahead and switch that around to look more like that. So it's a 1 over x plus 2 plus 2. So we have h is 2 and k is 2. Now, what we already learned from before, this creates some new asymptotes. So our new asymptotes are going to be at x equals negative 2 Now notice what that did. The asymptote used to be at 0 and now it's to the left 2 places. That plus 2 right there, what that did is that moved things to the left 2 places. And then k tells us that our new asymptote should be up at y equals 2. Now it used to be at 0, so that tells us to move up 2 places. So notice, just looking at these numbers, we can also say the way it moves the graph. Okay, and then past that, we know that it's just going to get closer and closer to those asymptotes. And there we go. We've graphed it. By being able to see that we can change it to this format if we just use some synthetic division. And now it's in a form where I know exactly where my asymptotes are. I know how those asymptotes have now shifted the function to the left 2 and up 2. All right, now let's look at a word problem. This company purchases a blueprint plotter for $1,500. The plotter costs for each set of blueprints is $25. So every time you make a new set of blueprints, that basically costs $25 to do once you have the machine. So our first question is, how many blueprints do we need to plot for the average cost of blueprints to fall to $75? Okay, so average cost. Average means we add up all of the costs. So this is a sum sign. It means to add them all up. So we add up all of our costs, and then we divide by however many there were. Okay, so if we only made one blueprint, then that would have cost us $25 for the blueprint, but we also still paid $1,500 for the machine. So our average cost, because after we add up all the costs, would be $1,525 for one blueprint. That would be our average cost. Now, the more of these we print, even though the cost is going up, the cost is being spread out among more blueprints. So the average should fall. So let's go ahead and write an equation for this. We pay $25 for each blueprint, X. So if it's one blueprint, then X is 1. If it's two blueprints, X is 2, and we paid $50 for those, and on and on and on. Plus the $1,500 for the machine. We need to divide it by the number of blueprints we make, which was X. And we want to know when that is going to equal 75. Okay, now right here, we are starting to see a function. We even have our A, B, C, and D would be 0. But let's not worry too much about that right now. Right now I want to know, what does X need to be for the average to be 75? So I'm actually going to be solving for this. First, let's multiply both sides by X, and we will get 25X plus 1,500 is equal to 75X. Next, if we minus the 25 from both sides, we get 1,500 is equal to 50X. Divide both sides by 50, and X is 30. So we would need to make about 30 copies for the average cost of blueprints to drop down to 75. This question down here, I want those to stay still. All right. So what happens to the average cost as more blueprints are plotted? Here's where I really want us to think about our graph. Okay, so if we look at what we have here and we use the information we got before, we know that we should have a horizontal asymptote that's going to be at about 25. Okay, and we will have our vertical asymptote be just at 0. Okay, you can't have an average cost for a blueprint if you never printed a blueprint. Okay, so thinking about the way this graph would have looked, over here we'd have that. Now that doesn't make much sense because this is saying we're printing negative blueprints. So that section of the graph doesn't make much sense. However, over here, we noticed, like what we saw before, if we only made one, the cost was super high. The average cost, if you only print out one, was $1,525. But the more we cost, it started coming down. And as we made 30 copies, we were down to it being an average cost of 75. This is going to continue to drop. And it's going to continue to get closer and closer to 25. But it's never actually going to reach 25. 25 is the smallest amount we pay per blueprint, and we still have to calculate in the cost of the whole machine. So the more there are, the closer we get to 25, but we're never actually going to reach that average of 25. It's always going to have cost us, on average, a little bit more than 25, no matter how many of these we make. Okay, I hope this helps you. Good luck.